Hello, everyone. Okay. Hello, everyone. First of all, I would like to actually thank you for this invitation. I'm very happy to have this talk. And today, I'm going to talk about a recent work that we did with Astrid and Aaron some months ago that you can find actually on arXiv with this following code. And it revolves around quark and lepton mixing in the standard model and how we can extract some kind of predictions or explanations of the structures of these mixing matrices in the standard model by coupling it with asymptotically safe quantum gravity. So just to introduce a little bit on how we are going to work towards this, I'm going to explain how asymptotic safety can lead to some predictive settings in the standard model, in the matter sector and the standard model. So usually, one tries to calculate the ERG flows and the gravitational contributions of the standard model couplings together with asymptotically safe quantum gravity. And these are usually taken this schematic form, where you see here that the gravitational contribution is introduced by a linear term in the matter couplings. This is the most usual type of contribution, and it's there at leading order. And then you also have this second part, which is a perturbative one loop result. And here and throughout this talk, we're going to add the pure matter part as a one loop beta function, because these contributions are universal. So they are also can come from an FRG study of the standard model together with gravity. Now, the important part here is that this gravitational contribution is identical for all gauge groups and flavors, because gravity does not really distinguish between different quarks and does not distinguish between different gauge groups. This FC will be the same for all gauge couplings, and then for all Yukawa couplings. Of course, I mean, between gauge and Yukawa couplings, this will be different, but the same type of interaction will have the same type of contribution. Another important thing is that you can think of this gravitational contribution as a function of the gravitational couplings, the dimensionless gravitational couplings. And specifically, this FC is also at least linear in the Newton coupling, and generally depends also on other gravitational couplings, like the cosmological constant. This kind of dependence actually allows us to use a more phenomenological approach and approximate this gravitational contribution as a constant above the Planck scale. Of course, if you have asymptotically safe quantum gravity, this is valid because above the Planck scale, you're reaching this interacting fixed point. And below the Planck scale, you can use actually the scaling of the dimension Newton coupling, which is quadratic in K, and you can argue that this FC quickly vanishes towards zero. So all in all, these two observations allows us to approximate this function FC as a constant, which we will also denote as FC here, times a step function, which will turn on and off the coupling above and below the Planck scale, respectively. So now I would like to actually say how this kind of gravitational contributions play out in the standard model. And the simplest example is the abelian hypercharge. At one loop, this is quadratic in the GY coupling. And here we have a gravitational contribution FG. Now, several FRG studies have shown that this FG is positive. And so the diagram, the phase diagram of this GY coupling, this abelian hypercharge, has this following form. And you can see here that there is an interacting fixed point corresponding to this green trajectory, where in the UV it remains constant. And if we emanate from, if a trajectory emanates from these interacting fixed points below the Planck scale, it can flow towards an infrared value. Here you can also see different trajectories. So if the coupling, if you are in a trajectory below this critical trajectory, which is the asymptotically safe one, then you are having asymptotic freedom. Or if you are above it, then you're hitting a Landau ball. Now, another way to think about this problem is, what if we fix the infrared values such that we only pick trajectories that are compatible with the standard model? In such a way, we'll pick one trajectory that connects some UV completion, either the Gaussian fixed point or the interacting fixed point, and we'll connect it to the standard model by fixing the infrared value to its experimental value at the electroweak scale. Here, this infrared scale will always be the electroweak scale. And now, by fixing this condition, we can actually play with the parameter and see if we increase it or decrease it, what happens, and how is the trajectory behaving in the UV. So, of course, you can have this trajectory, you can tune this parameter St so that this trajectory is the asymptotically safe one. And this is the value that you need to get in this case. But if you're above this critical value, then your trajectory will be the asymptotically free one. And if this because the gravitational contribution is more screening, and if this Fg is smaller than this critical value, then you're necessarily emanating from a Landau ball. So actually, this trajectory here will not be UV complete. So this is the simplest case. And this trajectory, the asymptotically safe trajectory, is called predictive trajectory because it fixes the value of the abelian hypercharge at the Planck scale. And so if you flow to the infrared, you will have a unique value in the infrared, which will be your sharp prediction. So if we set this value for the Fg, then we have tuned our system in such a way such we have a prediction for the abelian hypercharge. Now, the standard model also has more couplings. It has also Yukawa couplings and so on. So I would like to talk a little bit about also the Yukawa couplings. And here, this schematic form that was also introduced 2 weeks ago by Manuel is actually cubic. And if this Fy is positive, then the Gaussian fixed point is relevant because the fixed point, the critical exponent is positive. And so if we emanate from this Gaussian fixed point, we can generate some finite values of the Yukawa couplings. Now, if this Fy is negative, the Gaussian fixed point is relevant. And so this fixed point necessarily predicts that Yt equals 0. And this is, of course, not the phenomenologically viable scenario. Now, several studies have happened in the past regarding the sign of Fy, and more or less they saw that the sign of this Fy depends on the precise values of the gravitational fixed point. And for minimal matter content, so for small number of fields, it has been actually shown. There are some results that show that this Fy is negative, and which will be the phenomenologically unviable case. But there is also some other values where for a larger number of fields, we actually do not really have a concrete result regarding the sign of this Fy. But let me mention here this very recent result by Gustavo, Manuel, and Mark, where they highlighted the fact that this Fy is not the critical exponent actually for the Gaussian fixed point if we consider next to leading order operators. And so their calculations show that these Yukawa couplings are relevant when we increase the order of the computation. And so the standard model can emerge actually from the Gaussian fixed point. And how does this look like? In the study in 2022 by Alvaro, Manuel, and Jan, they actually constructed a trajectory that emanates from the Gaussian fixed point with Fy positive and Fg positive, such that they can get the standard model to emerge from such a configuration. In this specific model, all couplings are relevant, so there is no extra prediction. But what we would like to achieve here is we would like to see if actually the standard model can emerge from another fixed point and potentially give us some explanations, some predictions, some more structure. And this is where we are aiming for. And especially we're aiming to actually describe the quark and lepton mixing in the standard model. So now that I've mentioned also quark and lepton mixing, let me spend some minutes and actually introduce to the uninitiated what actually quark and lepton mixing is. So in the standard model, as you might have heard, there is this gauge group of SU3 cross SU2 left cross U1Y, which is the fundamental gauge group of the standard model. And here we have the Yukawa Lagrangian of the standard model, where Q is a doublet that transforms in the fundamental representation of SU2. And this DR and UR corresponds to the down-type quarks, the red-handed down-type quarks, and the up-type right-handed quarks. And H, of course, is the Higgs doublet, which transforms also in the fundamental of SU2. And here, the important thing is that these Yukawa couplings is not actually one Yukawa coupling for each quark, but these are 3x3 matrices. So these by 3 matrices do not actually connect only same type quarks, but also they also introduce some mixing in between them. Now, this kind of parameterization has 9 plus 9 parameters inside. However, these actually are not at all of them independent, and there is some very redundant description here. And in order to minimize a little bit the redundancy and have a more concrete view, we would like to actually change bases. And instead of talking about flavor eigenstates of the quarks, we would like to have the mass eigenstates of the quarks. So instead of having general Yukawa couplings, we would like to have Yukawas that enter the masses of the quarks and also some extra parameters, which will be actually the mixings. And after you do this change of variables, you end up with a Yukawa Lagrangian that is diagonalized, where you have 3 couplings YDI, which will give the masses after spontaneous symmetry breaking to the down-type quarks, and these are Dirac masses. And you have also 3 couplings YU that will give the masses to the up-type quarks. But where are the rest of the parameters of the Yukawa matrices? These are coming from the kinetic terms and the gauge fermion vertices. So if you calculate a vertex like this one, you will see that it is proportional to a matrix element, which is given by this definition here, which involves this unitary transformation from one basis to another. This matrix is by construction unitary, and it depends only depends only on 4 parameters. So totally, we have 3 Yukawa couplings that will give the masses to the down-type quarks, 3 for the up-type quarks, and 4 mixing parameters that can be parameterized in a more standard convention to 3 angles at 1 CP violating phase. The most crucial part that I actually want you to take from this is that the gravitational contributions do not enter the flows, the one-loop flows of these mixing parameters, and the gravitational contribution only see the masses, the mass parameters. And this is, of course, because the gravitational contribution does not really see any mixing effects at the fundamental level. So now I would like to actually show you how this CK matrix looks like to an experimentalist. And I think the most useful way to see this is by taking a matrix with the square of the CK matrix element. Why I think this is the best way to actually explain what we have to explain is because actually the squares of these elements enter the beta functions of the Yukawa couplings, and also because unitarity, the demand that this CK matrix is unitary, is very can be expressed in a very easy way, simply by summing all the elements of each row, and then each row will sum to 1, and of course also its column will also sum to 1. So unitarity actually relates all of these elements, and in reality we have only 4 independent parameters, which we will take to be these 4. The 1, 1, 1, 2, 2, 1, and 2, 2 elements. So now experimentally, what are the numbers that we actually try to explain. And you can find them in the PDG report from 2024. And these numbers are really nice. You can see that the diagonal entries are way, way bigger than the off-diagonal entries. And schematically, the size of these couplings, which its maximum, of course, is 1, can be actually seen in this kind of cartoon, where you see that the diagonal elements are way, way bigger. And of course, these two elements here are orders of magnitude smaller than all of the other ones. So here we have some structure, a near-diagonal structure, that we would like actually to explain. So the precise question that we wanted to ask is, can this structure emerge from some RG flow? And this question, we're not, of course, the first to ask these questions. This has been already thought about in the 80s, where already people realized that in specific type of limits, you can have this diagonal configuration to be infrared attractive in RG flows. However, there is a real problem here. And in fact, if you try to calculate the RG flow from the electroweak scale to the Planck scale, you see that the CKM metric doesn't really run. Like it runs really, really slowly. So you don't really have enough flow or enough time to actually reach this configuration. So here we actually need to do more. And this there was this idea, and that was based also in an observation, that we can actually calculate have this emergent structure from asymptotically safe quantum gravity. And the observation is as follows. If you take these two numbers here and you sum them, then you find up to 10 to the minus 5 accuracy that they sum equal to 1. And if you do the same for the second column, you also find the same. And of course, unitarity will lead to these two numbers to be really, really close to 0. So you will ask now, okay, so what? And the main thing here is that actually this relation, this experimental facts, satisfy these following relations, where the VUD is 1 minus VUS, the VCD is 1 minus VCS, and VUS is equal to VCD. And these relations are special because they actually correspond to an infrared attractive fixed line in the RG flow of the CKM matrix in the heavy top limit. So actually, we observed here that the experimental data, instead of indicating just the diagonal structure, they indicate that the experimental values satisfy relations that are from an infrared attractive fixed line. And we would like actually to engineer a system where we can actually flow towards this line. And this line was first already found by Astrid Aron and collaborators in 2020. So what do we need to do is, of course, a top regime. So a top dominating regime. So there are two options here. The one way to actually proceed is that we actually say that these relations are just a coincidence and QFT does not hold above the Planck scale. Or we can be a little bit more bold and say that the QFT holds in scales way beyond the Planck scale, and also that there is a top dominated regime where we can actually flow towards the infrared fixed line. And I mean, from this mean, you can understand what we are trying to do here. We don't believe that this is a coincidence. So we are going to try and see how this plays out. So the trick here is that asymptotically safe quantum gravity actually allows us to extend the flows beyond the Planck scale towards a top-dominated regime. And here you can see this by checking the beta functions for the top Yukawa coupling, but also the full beta functions that include also a term which is negative and depends on the abelian hypercharge. So here we can have the following scenario. Since Fg is positive, we can have the abelian hypercharge to become asymptotically safe. In that scenario, the Gaussian fixed point is no longer irrelevant for Fy is negative, but it acquires, the critical exponent acquires a positive contribution, which allows the Fy to be a little bit negative. So in this case, the Gaussian fixed point is actually relevant if we choose Fy not negative. There's also this case, the phenomenology of this case was also has been explored before in the Quark setting and also in the lepton setting by Acid and Aaron and collaborators in 2020 and by Kamila Kowalska's group in 2022. But the most important fact here is that there is actually a fixed point for the top Yukawa coupling, which takes this form. So the top Yukawa coupling can be non-zero in this fixed point, and all of the other couplings, including the bottom, I'm just writing the bottom here, they are actually zero. And the important thing to consider there is, of course, the critical exponents. And it turns out that both directions here are irrelevant. So this is also good and bad, because if the top direction is irrelevant, then it means we can have a prediction and we can actually flow towards the top dominated regime. However, if the other couplings are irrelevant, then this means that this fixed point will actually predict that all of the other quarks are zero. So actually, this fixed point cannot provide a UV completion, which is compatible with experiments, because we know that all of the other quarks have also non-zero masses. So what can we do is, again, we want to actually check if the if the standard model trajectory can actually go there. And we observe here that if the YB is irrelevant and non-zero in the infrared, then the flow will float. If we take the flow towards the UV, at some point, the bottom Yukawa will become dominant. And if it becomes dominant, we can have also another limit, the bottom dominated limit, where we can even find a fixed point. And the fixed point actually looks like this, where the bottom is non-zero and all of the other quarks are zero. But here, you see something crucial. The fixed point is actually smaller than the top dominating one. And this means that the bottom Yukawa YB is irrelevant, which is nice because we retain some predictivity that we actually wanted. But also, and most importantly, all of the other vanishing Yukawas are relevant. So actually, this fixed point can be a true UV completion of our theory that wasn't considered before. And we can actually emanate from this fixed point towards some standard model infrared configuration. Now, how is the mixing matrix in looking in this UV fixed point? We can find that this relation, YUD, VUD, VUS equals 0, and VCB equal 1 minus VCD, this fixed line, is actually has actually 3 relevant directions and 1 marginal. So you can take that all of this coupling will flow away from this fixed line, apart from this marginal direction, which also indicates that this is a line. So here we found the UV completion. How does it look like? We did some numerical integrations, and it looks like this. We have, of course, named this kind of setting as the top-bottom cascade. And here you can see we can start from the UV, and we can flow towards in the infrared, cascading from the bottom fixed point to the top fixed point towards the standard model values in the infrared. And we can also do this for the CKM elements, which actually reveals us very nice things that we are going to talk about them right away. So the next few minutes are going to be about this bottom plot, and we are going to try to deconstruct it. And the first thing is we are going to check the second row of the CK matrix and see how it flows. So you see here that VCD and VCS are flowing to 0. And this means that these are the VCD, VCS equals 0 are irrelevant directions. They are attractive. However, there is also the relation 1 minus VCD square minus VCS corresponding to the VCB, this element here. that we actually want to achieve the near diagonal structure, we actually want it to flow to zero eventually. However, here you see that this corresponds to a relevant direction in the bottom dominated regime. So this relation is actually growing as you flow towards the infrared, and below the transition scale, it goes relatively quickly to zero. Now, this plot by itself doesn't tell you much until you actually compare it with the other relation. So we go to the first row and see that, of course, the VUD and VUS are relevant directions because they emanate from this UV fixed line. But the relation of the VUB is actually VUB equals zero is an attractive relation, which means that the relation that we wanted to achieve in the infrared to explain the CKM matrix is actually already attractive in the bottom dominated regime and continues to be attractive also in the top dominated regime. And you can see this here if you take this bottom heavy bottom limit for the beta functions of the VUB. So if we combine these two, sorry for the animation here, but if you combine these two plots, you see here that one relation flows towards the experimental value that we would like to explain for way, way longer than the other relation. And this is actually reflected in the experimental data, because the VUB, which is the magenta, is equal to zero up to an accuracy of 10 to the minus 5, and VCB is goes to zero up to the 10 to the minus 3. And actually, because the errors are very, very small, we are actually sure experimentally that VUB is way smaller than VCB. And this structure, this relative accuracy of the CKM elements is actually explained by our top-bottom cascade. And we interpret this as a fingerprint that it is encoded in the experimental data. So this is one of our main results. And now we would like to see what happens when we include the lepton sector into the picture and bring everything together. So if you would like to add leptons into the picture that are also lead to some massive neutrinos that we know that are massive, you can do it in various ways. And in here, we introduce 3 flavors of right-handed neutrinos with Dirac mass terms. So here you have an identical structure for the Yukawa-Lagrange for the lepton sector with 2 Yukawa matrices. And the main thing that I want you to see is that this structure looks identical, and there is actually a mapping between the quarks and leptons that reproduce the exact same flows. So if you map the up-type quarks to the neutrinos and the down-type quarks to the leptons, following the standard convention of the electroweak doublet, then you obtain the same exact flows. And this is a priori maybe a problem, because if we find that the PMNS matrix has some significant running, then since the flows are the same, the flow cohesions are the same, we would expect to also have the same kind of structure for the PMNS matrix. And people might be happy because, like you say, okay, I will also explain the PMNS matrix with the same type of idea. But here, the experimental data will come and haunt you, because actually the PMNS matrix is very far from being diagonal. And so we have to be a little bit more careful here and somehow ensure that the PMNS matrix does not converge to this configuration. And how does this happen? Is we can see how this might happen by checking the flows of these 2 elements that we also focus in the CKM matrix. So this element has this following beta function here. This is denoted as new electron neutrino tau. And here you see you have the same structure here with the tau lepton instead of the top. But here you also have this combination here, which is exactly the same also for this element. And the main thing here is that if you have a flow that leads to big neutrino Yukawa couplings, then this combination can become really large, So the critical exponents will become really large, and the PMNS might start running. And this would correspond to the near degenerate case, which will lead to the PMNS running. And actually, the near degenerate case is exactly what we want to avoid if we don't want to have contradicting results. So here, how does this play out in our top-bottom cascade? Here you have a top-dominated regime where the neutrino Yukawa coupling has a critical exponent that is very small, but it is negative. And in the bottom-dominated regime, you have a neutrino Yukawa coupling with a critical exponent that now is positive. So here, you expect in the bottom-dominated regime, the neutrino to flow towards the infrared to very, very high values with the danger of going too large so that the PMNS starts running. However, then the top-bottom dominated regime comes to the rescue and drives down the neutrino Yukawa coupling towards small values again. Or if you want to view the flow from the infrared to the UV, if the top-dominated regime is too long, then as you flow from the infrared to the UV, the neutrino Yukawa coupling will grow large. And if the top-dominated regime is too long, then you might also have, again, a significant running. So here we have a mechanism, essentially, that says that neutrino Yukawas in our model can remain dynamically small throughout the cascading RG flow, which is a similar mechanism that was found in 2022 by Aaron and Astrid in a slightly different setting, where actually it's a very different setting, because the top and bottom Yukawa in this setting become asymptotically safe in the same kind of regime. Another mechanism you can find for the same type of thing, where the neutrinos remain small, in another work by Kamila Kowalska's group, also around the same time. But how does this lepton sector now looks after numerical integration? You can see them in this plot, where you see here that if we start from very, very small values of the neutrinos are flowing very, very, very slowly. And at some point below the transition scale, will start decreasing again, so that they remain very, very small compared to all of the other couplings. Also, the charged lepton are growing throughout the flow, and they are relatively way faster than the neutrinos, but still they are remaining so small that effectively the whole flow of the PMNS matrix is actually so slow that even if you run for thousands of orders of magnitude, you see here that the PMNS elements are precisely kind of frozen. So here in our lepton sector, we have that if we view this from the infrared to the UV, because we fix the infrared values to the standard model, we see that the lepton sector runs quickly to tiny values, and the neutrino Yukawa couplings runs very, very slowly and remains tiny. And as a result, the PMNS matrix does not run. So there is no emerging structure if we embed the lepton sector in this top-bottom cascade. And this is actually very nice, because we can actually say that, you know what, these values of the PMNS matrix, they seem kind of random because they kind of are random. You're fixing some values in the UV, but there is no significant flow that will lead you to some emergent infrared structure. So now I'm coming towards the end of my talk, and I would like to a little bit sum up all of these things that I have explained in a single plot, where basically we have shown that we can have a UV completion with an Fy that is slightly negative, that emanates from a UV fixed line from a bottom-dominated regime towards a top-dominated regime. And the fixed line is, of course, in the CKM elements. And if you flow from this fixed line, you're naturally flowing to this infrared attractive fixed line, which explains the structure of the CKM matrix. In fact, the elements of the off-diagonal elements scale differently in the different regimes, with VCB growing in the bottom-dominated regime and going towards 0 in the top-dominated regime, while the VUB, which is in the first line, flows towards 0 in both regimes, leading to some imprints of this kind of flow to the experimental data that shows that VUB is way, way smaller than VCB square. And on top of that, we also have the lepton sector, which flows very, very quickly to 0, and the neutrinos remain small, with the result that the PMNS elements, so here the example is this magenta line, remains essentially frozen. So all in all, we have that the near diagonal structure can emerge as from RG flows towards infrared fixed line. And this can happen by assuming some trans-Planckian quantum scale invariance, so allowing the QFT to hold for very, very, very long scales. And in this specific top-bottom cascade, we can actually achieve the structure. And the PMNS, which has no apparent structure, must not run. And so the neutrinos must remain small. And as a finishing slide, I would like to present you the outlook, which is basically the current work in progress. And we are planning to actually investigate the phenomenology of other UV completions and essentially works towards having a full catalog of all the possible UV completions from which the standard model can emerge in the space of this playing with this coupling, where F lambda is the gravitational contribution to the Higgs quartic coupling. Another very exciting prospect here is relies on the fact that the PMNS must not run. And with this idea, one can extract a neutrino mass bound that is independent of any UV completion. And here you can see a preliminary plot that you can also find in the paper, where showcases this idea, where if we assume that the PMNS does not run from the electroweak scale to the Planck scale, or that the change is like less than 10%, we can actually extract a bound on the electron neutrino effective neutrino mass, which is actually measured by the Catron experiment. And we can actually put some bounds to how big this neutrino mass can be, so that we cannot have significant running. And second of all, we would like to actually check how generic are these very predictive trajectories from random initial UV configurations. So basically, in this model, we have fixed the initial conditions such that we can actually have the standard model to be emergent from them. But we are actually interested to see what happens if we take a UV interval. How does this map to the infrared, to see how generic can the emergence of the standard model be? And to actually answer these questions in a quantitative way, one would have to employ this new way of thinking by studying the RG flows of distributions that were recently introduced by Astrid and Aaron some months ago. And with this, I would like to thank you very much.
Thanks a lot, Zois, for the nice talk.
Thank you.